Hey everyone, welcome back to our lesson on electrostatics. We're going to continue with this topic, and we're going to start talking about the law of conservation of charge, which is up here a little bit. And the law of conservation of charge says that if we look at a closed, isolated system, so nothing open to a surrounding environment, look at a particularly closed system, could be small, could be large, the total charge of that system is going to remain constant. And that's what the law of conservation of charge says. Charges can move, but overall, charge will be conserved. And we should have an overall charge on the system that remains constant. We don't create or destroy charge. It is simply transferred from one object to another, essentially infinitely, from object to object. And we'll take a look at a little scenario with that, with these three insulating spheres right here in this example. So we have three spheres labeled R, S, and T with three different charges. R has no charge, S has -8 charge, and T has a +6 charge. Now what I want to do here is look at the net charge on this system, or the net charge to start. Well, try and keep that somewhat straight and organized there. So look at the net charge to start, and we're going to take the value of each one of these insulating spheres. We're going to add a -8. That E is elementary charge, which is on your reference table on the front page. We have a +6 elementary charge. If we add up the charges of these three spheres, we get an overall net charge of -2e. And this is to start. Now, law of conservation of charge says no matter what we do here with these spheres, we should maintain this overall charge in this system, assuming it is closed or isolated. We should maintain a charge of -2 elementary charges. So it says, what is the charge on sphere T after sphere R is brought into contact with sphere S, removed, and then sphere S is brought into contact with sphere T and removed. And then let's explain. So we did something similar in class with the demonstration with the glass rod and the fur to transfer charge. And the same idea is going to apply here. We want to keep in mind that we're going to conserve all of our charge. So first thing it says, sphere R is brought into contact with sphere S. Now when we bring R into contact with sphere S, the total charge between those two, we had 0e plus a -8e. The total charge there is -8e, but this is going to get divided. This is S here. The -8 charge will get divided amongst those two spheres when they get brought into contact, and each one, after removal, should have a charge of -4e. So after the change, what we have here, I'll do R first, then we'll have S. These have been removed. We're left with 4e, 4e, and that is -4e. So each of those spheres, after coming into contact, their charge splits evenly. We separate them. Now each sphere, R and S, has a charge of -4e. We still have sphere T here. And it says that we remove it, and then sphere S is brought into contact with sphere T. And sphere T, we're going to bring this into contact here with sphere S. And what's happening here, we have a charge of a +6e on T and a -4 charge on S. this gives us an overall charge of a positive 2e. Now when we separate T and S, this charge will distribute evenly amongst those two spheres. So we look at the average there. This comes out to an average of 1 elementary charge, 1 positive elementary charge. And this will get distributed evenly amongst these two, where we have T and we have S, and each one of these will have a positive E charge. Now the charge on sphere T would be our positive E value. And just to confirm that this is right, we started with an overall charge on this system of minus 2e. So if we check our work here amongst these three spheres, S, T, and R, and we're going to look at R, S, and that kind of grayed that out. That doesn't look very good. See if I can just get the highlighter there. I'm not going to be able to. So I'll do this. We're going to look at the conservation of charge amongst these three spheres. So what we have here from R is a minus 4e, and on T and S we have a positive E and a positive E. And this comes out to a total of minus 2 elementary charges. And if we compare it to what we started with, this remains the same. So we conserve charge between the spheres. When coming into contact, charge is distributed evenly. When separated, each of those spheres maintains that charge until it is brought into contact with something else. Now what this doesn't really account for here in the real world is that this is done as a demonstration or in a lab. Even though we're not coming into contact with the spheres physically with another sphere or maybe another object, charges still can be lost to the environment through the air. So that's a little potential losing point here for conservation of charge, or an idea of where charge could be moving when something's not, we're not thinking of it as being in contact, but it is with the air. We're going to talk next about the quantity of charge. And the SI unit for charge is the coulomb. I come across a lot of different new vocabulary. This is represented with a capital C. And 1 coulomb is equal to, not quite Avogadro's number, but close, 6.25 times 10 to the 18th power elementary charges. And we're going to find each of these on the front page of the reference table. And it's under the physical constants. So the charge on an electron from the reference table, we know it's a negative charge. It's a negative. I'm going to draw that clearly so we don't mistake in that. It's a negative 1.6 times 10 to the negative 19 coulomb. A pretty small charge value. And the charge on a proton is going to be exactly opposite that. Equal in magnitude, opposite in direction. 1.6 times 10 to the negative 19th coulomb. So same charge, opposite direction. Same magnitude, opposite direction, indicated by the positive and negative value. Now, Coulomb's law. Coulomb's law we're going to use to determine forces that are occurring between different charged objects, usually dealing with point charges or simple electron or proton type charges, and how the forces between them are going to act. And what it says is that it's going to vary inversely to the distance between those point charges. This is going to be all over the distance squared. We measure that electrostatic force, as with any force, in newtons, which would be F sub E. Q1 and Q2 are going to be the charges that are going to be in coulombs. And R is the distance of separation in meters. And generally these are pretty small numbers. This is going to be meters squared. Now K is our electrostatic constant. And it's equal to 8.99 times 10 to the 9th newtons times meter squared per coulomb squared. And this is again on the reference table on our list of physical constants on the front page. So you can find all that there. A lot of our other information that we need from the reference table that has to do with electricity and magnetism is all on page 4. So we kind of move away from our mechanics equations on the last page. And most of what we'll use for this unit is on page 4, starting with Coulomb's law as the first list of equations given there. So we'll use that and we'll practice with that in class to measure force between two different point charges. Now the size or magnitude of the electrostatic force, F sub E, between two point charges is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. So as we start to move two point charges away from each other, the force decreases exponentially as that distance between them gets greater. We'll dive into Coulomb's law a little bit more in class, do a little practice with Coulomb's law as well. If you have any questions, make sure you write them down and be sure to ask them when I see you in class next. Have a great day, everyone.